In simple harmonic motion, today we are going to deal with the problem of simple pendulum. Actually, this is a very important problem of classical physics, and this idea is used at various places. So, what is actually the plan of the study of this simple pendulum? What we will deal in this problem? First of all, we will know what is this simple pendulum. After that, we will discuss the motion or nature of motion of this simple pendulum. You will see that actually in a small oscillation limit, this pendulum executes simple harmonic motion, or particularly you can say the angular simple harmonic motion. So we will deal the problem of simple pendulum as a angular harmonic simple harmonic oscillator, and finding its equation of motion or the restoring torque acting on it, we will be able to find its time period and frequency. Okay, and actually the time period of this simple pendulum depends on three factors. First one is its amplitude. If amplitude will be small, then what will be the time period? If amplitude is not small or the angular displacement is not small, then what will be the time period? Again, what is the length of this pendulum? That also affect the value of time period. So first of all, we are going to see the discussion of the motion of this simple pendulum when its length is much smaller than r, where r is actually the radius of the earth. Okay, and its angular displacement theta is very small. Under these two limiting conditions, first of all, we will discuss the motion of the simple pendulum. But after getting the result for this situation, we will relax these conditions, and then we will again see what will be the time period of this simple pendulum and what type of oscillatory motion it will execute. Okay, so this is our plan to study this problem of simple pendulum. So first of all, I would like to define what do you mean by a simple pendulum. Actually, a simple pendulum is defined as a point mass suspended by a massless inextensible string from a rigid support, okay, which oscillates about its equilibrium position under gravity. As you can see in this figure, that S is a rigid support, and I have suspended a point mass having mass m, and in equilibrium, this point mass, which is also called bob of the pendulum, is at this point B. Actually, when the bob is at point B, then net force on it will be 0, because in this condition there will be two forces acting on the bob. One will be its weight, that is force of gravity mg, which acts in downward direction, and another will be the tension of the string. And actually this T balances mg and the resultant force is 0. So this point B is called equilibrium position. Okay, so the point mass oscillates about this point B. But in definition, I have used two terms. First one was massless string, okay, and again I have told that this massless string, from the massless string a point mass has been suspended. But these two terms which you used, or these two properties, are not found in practice. You have not any string which is completely massless, and if there is a mass, definitely there will be some dimension. So massless string and point mass, these are actually the ideal situations, and so we can never construct a simple pendulum strictly according to the definition. So actually in practice, we take a heavy spherical mass which is called bob and suspend it from the light inextensible string. So at the place of the word massless, you should use light in practice. Okay? And at the place of point mass, we have a small spheres. A small spheres. A small sphere. Okay? But in definition, we say that a point mass suspended by a massless inextensible string from a rigid support which is capable of oscillating about its equilibrium position, that is called a simple pendulum. Okay. You can see this figure. Actually, in this figure, I have shown the small sphere suspended from point S by a light string, and in equilibrium position the ball is at point B, and when, let us say, it is displaced from point B and bring to the point A, when the string makes an angle theta naught to this vertical line SB and released, then due to the force of gravity, a restoring torque acts on the bob, and that torque actually tends to bring this ball towards the point B. So the ball will return to the point B, and at point B the torque will become actually 0, and in that condition the ball will not stop. Due to inertia, it moves towards D. Okay? But as the ball is moving towards D, the torque now acts again towards B and its velocity decreases, and at point D it becomes 0, and after that it returns back. So in this way, this bob oscillates about the equilibrium position B. Now, to get the equation of motion of this oscillatory motion of the pendulum, let us consider an arbitrary position C where this bob is at any time t. Okay? And at this time, the string SC of the pendulum makes an angle theta to the vertical line SB. So this theta is what? You know, this is angular displacement. Theta is angular displacement. Okay? And here, what are the forces acting on this bob? You know, one force will be its weight, that is force of gravity, which acts in vertically downward direction. If you consider that length of the pendulum L is much smaller than radius of the earth, then we can take that mg is always directed in vertically downward direction. Okay? So I have taken mg directed towards the vertically downward direction. And another force is the tension T, which passes through the point of suspension. Okay? Now this force mg will constitute a torque, but torque due to this tension T will be 0. Why? Because this force T, the line of action of T is passing through the point of suspension, so its perpendicular distance from point S is 0, and so torque due to tension T will be equal to 0, because you know torque is simply equal to R cross F, and here R will be actually equal to 0, or you can say R will be parallel or anti-parallel to F, and so this will be equal to 0 for tension. But this mg will constitute torque. What will be the torque constituted by mg? You can see the perpendicular distance of this line of action of force mg from the point S is equal to CE. This is called moment arm. So tau will be equal to mg times Ce, mg times Ce. But this torque has a tendency to decrease this theta. It means this torque tends to bring this sphere or bob towards point B. So considering this sense of the torque, we put here minus sign. So we will write torque tau is equal to minus mg into Ce. Okay. All these calculations I have done here, you can see, and the concept which I have just discussed, I have also written here for your convenience, because in your university examination particularly, you have to write down these languages too. So for your convenience, I have written all those facts. Okay. As you can see, I am just giving a reading. A point mass suspended by a massless inextensible string from a rigid support oscillating in a vertical plane is called a simple pendulum. And in note I have written, neither a point mass nor a massless string exists, so simple pendulum cannot be strictly constructed. A small heavy spherical mass suspended from a light inextensible string constitutes an approximate simple pendulum, as I have explained just now. Okay. And then you have seen that when this bob is displaced, this bob actually describes a circular arc, or it you can say that this oscillates along a circular arc in a vertical plane. Now see what will be the value of the torque. As you have seen, tau due to tension is 0. So only the force of gravity constitutes here torque, and that torque is given by tau equal to minus mg into Ce. Now see the figure and try to find what will be the value of Ce. This Ce, you can find it from this triangle SCE. As you can see, if you write sine theta from that triangle, what will be sine theta? That will be Ce and divided by SC. Ce divided by SC. Okay. And this is Ce divided by L, because SC is equal to length of the pendulum. And therefore you can see this Ce will be simply equal to L sine theta. This is equal to L sine theta. Okay. So I have written here at the place of Ce L sine theta. You can see it here. So we find that the restoring torque acting on the bob is equal to minus mgl sine theta. What is the significance of this minus sign? As I have told you earlier, that this negative sign is used as direction of the torque is opposite to the displacement. So we write here minus sign, and this actually represents the restoring nature of the torque. Okay. Now, the value of sine theta will depend on the value of theta. As I have told you earlier, first of all, we will consider the case of a small oscillation. When you say a case of a small oscillation, what does it mean? It means we displace the bob from the equilibrium position slightly. So when the oscillation takes place in the close neighborhood of the equilibrium position, then it is called case of a small oscillation. So in case of a small oscillation, this theta will be very small. Okay. And you have definitely studied in calculus that limit theta tends to 0, sine theta is equal to theta. What does it physically this equation means? It means when theta is very small, then sine theta is equal to theta. So in this limiting condition, when we consider the case of a small oscillation, that is oscillation of the bob near about the equilibrium position, then theta will be very small, and we can approximate sine theta equal to theta. Okay, so let us substitute sine theta equal to theta in the expression for torque which we have obtained earlier. So what will be not this tau? Torque tau will be equal to minus mgl theta. As you know, mass m in classical physics is always constant. G at a given place of the earth is also constant. And since our string is inextensible, so L will be constant. So completely this product mgl is constant. So except theta in RHS, mgl is constant. So instead of mgl, we can put C. Okay. Actually this C you have studied, this is called torsional constant. So tau is equal to minus C theta. So how this tau is related to theta? You can see actually this tau is proportional to minus theta. Okay. Or you can say if you will plot a graph of the magnitude of this tau, it means we are neglecting the minus sign, then we will have a straight line passing through the origin. And you know, if torque acting on a particle is a linear function of angular displacement, definitely the motion will be angular simple harmonic motion. This is the necessary and sufficient condition for angular SHM as you have learnt in the previous lecture. So this equation tau equal to minus C theta implies that the motion of this pendulum will be an angular simple harmonic motion. And as in the previous lecture you have seen, if we know the value of C, we can find the time period. Remember that formula. I have told you, you have to remember the formula for solving the problem. You have learnt in the previous lecture that time period of an angular oscillator is given by T equal to 2 pi root over I by C. Okay, where I is the moment of inertia of the bob about an axis passing through the point of suspension S. And as you can see, if our bob is here and its mass is m and axis is passing through S, and the perpendicular distance of this bob of mass m from the axis of rotation is S. So what will be the moment of inertia? That will be simply ml square, because this mass m is just a point mass. Okay, and so at the place of I you can write ml square, and C you have seen this is mgl. So time period is found 2 pi root over L by G. So you can see only finding the torque acting on this particle, I have decided what type of motion the particle will perform. So up to this calculation, even up to this calculation, we can prove that the motion of this simple pendulum will be angular SHM, because tau equal to minus C theta, that is variation of tau linearly with theta, is the necessary and sufficient condition for angular SHM. Okay, and remembering this important formula, we can also say what will be the time period of this oscillation. And once you know the time period, if your aim is to find the frequency of oscillation, you will simply write it 1 over T, and that will become 1 over 2 pi times root over G by L. Root over G by L. Okay. But we can also prove that this motion of pendulum is angular simple harmonic motion by finding its equation of motion. Actually, we will find now the equation of motion of this pendulum, and we will compare the equation of motion with the standard equation of angular SHM, and you will see both will be same. And if your aim is now to find the equation of motion of this pendulum, what you will do? Actually, now we will apply Newton's second law of motion in case of rotational motion for getting the expression for tau. As according to second law of motion, In case of rotational motion, you know this torque is given by I alpha, where I, you know, this is moment of inertia of the particle about the axis of rotation, and alpha is its angular acceleration. Now, since theta is the angular displacement, and you know the second order time derivative of angular displacement is equal to angular acceleration. So, at the place of alpha, you can write d2 theta by dt square. Okay? And what is I? You know I is ml square. So, tau is equal to ml square d2 theta by dt square. But you have seen in the previous equation that tau is equal to minus mgl theta. You have seen. So you can equate these two values of tau. So ml square d2 theta by dt square, this will be equal to minus mgl theta. Okay. And now this m in LHS and this m in RHS will cancel out, and d2 theta by dt square will be equal to minus g over L theta. And as g and L both are constants, so instead of g of L, we now write omega square. Okay. So I have written omega square at the place of g by L. Okay. And so our resulting equation becomes d2 theta by dt square plus omega square theta equal to 0. Can you remember this equation? Definitely you can remember, because you have learnt this very important equation in your previous class, that this is nothing, this is simply the equation of motion of angular SHM. So what we are seeing here, you can see when we will compare this equation to the equation, standard equation of angular SHM, you will find that this is simply the equation of angular SHM. So after getting this equation of motion, we can definitely say that the motion of the simple pendulum is an angular SHM. Although some writers treat the simple pendulum as a linear harmonic oscillator too, but that is not very appropriate. That is not very appropriate. The appropriate fact is what? This oscillator is an angular harmonic oscillator. Okay. Now, omega square, you have obtained, this is g by L. So you can say that omega is a square root of g by L. And now, if your aim is to find the time period of its oscillation, you know time period and omega related by this relation, t is equal to 2 pi over omega. So time period of this pendulum will be what? This is 2 pi root over L by g. You can see after getting equation of motion, we find the time period. But there is when there will be a numerical problem and we have to show that motion is SHM or not, we can do calculation only up to equation 1a. Once you get that torque acting on the particle is a linear function of theta, that is in the form of this tau equal to minus c theta, you can say that the motion is angular SHM. There is no need to write the equation of motion. But in that condition, if your aim is to find the time period, you must remember this formula. You have to remember it. Only then you can find time period. But when you write equation of motion, then you get the value of omega. And getting the value of omega, we can easily find the time period. So these are the usefulness of the two approaches. Okay. Now, as I have told you, just in this calculation, that our discussion was limited in two conditions. There were two constants in our calculation. First one was L is much smaller than R. How you can say that L is much smaller than R? We have considered because we have considered that mg is always directed in vertically downward direction. It will happen only when we consider that the length of the pendulum is much smaller than the radius of the earth. And another limiting condition you have taken, that theta is very small. It means we are talking about the small oscillation. But what will happen when theta is not very small, but theta is large? Then what will happen? If theta is large, you know you cannot write sine theta equal to theta. In that condition, the torque will be what? The torque will be minus mgl sine theta, not theta. Okay. Now, you have definitely studied the expansion of this sine theta in your course of trigonometry, and you know sine theta is equal to theta minus theta cube over 3 factorial plus theta 5 over 5 factorial minus so on. Okay. And if you now take theta as a common factor, your result will be minus mgl theta times 1 minus theta square over 3 factorial plus theta 4 over 5 factorial minus so on. Now you can see in this condition, is this tau proportional to minus theta? Certainly not, because the terms or the series inside this square bracket, we can say that this restoring torque is not proportional to minus theta. It means when theta is not small, then the restoring torque is not a linear function of the angular displacement theta, but it is a non-linear function. And you know, if the restoring force is a non-linear function of angular displacement, then motion will be oscillatory, but not simple harmonic motion. So you can easily say now that in case of larger angular displacement, motion will be oscillatory, but it will be not simple harmonic motion. This is a very important fact. I hope you have clearly understand. Okay. Now I am writing a result here, but I have not proved it here. In fact, in the forthcoming lecture, when we will discuss the numerical problems, then I will derive this result. But here, for your knowledge, for your concept, I am just writing the result directly. Actually, it can be shown that if theta is not small, then what will be the time period? What will be the time period? After calculation, it has been seen that if we consider that in this case time period is t prime, I have considered time period by the symbol t in case of a small oscillation. So here I am considering time period by the symbol t prime. After making calculation, it is seen that this t prime will be what? Actually, in this condition, the value of t prime will depend on the amplitude of the oscillator. In fact, in case of a small oscillation, the time period you can see does not depend on amplitude. You can see the first figure here. This theta naught, this is maximum value of theta, and this is called amplitude. But when we consider the case of a small oscillation, time period is independent of amplitude of the simple harmonic motion. But in case of the large angular displacement or large value of amplitude, this time period depends on the value of amplitude. And as I have told you, I am writing here directly a result without any calculation, that if theta is not small, then time period t prime is found 2 pi root over L by G times 1 plus 1 over 2 square sine square theta naught by 2 plus 1 over 2 square times 3 square over 4 square sine 4 theta naught by 2 and so on. Okay. Here theta naught you have seen in the figure, this is amplitude of oscillation. Okay. And when actually you can see this 2 pi times root over Lg. What is this? This is time period of this simple pendulum in case of a small oscillation, which we have denoted by the symbol T. And the series inside this square bracket is almost equal to 1 plus theta naught square over 16. This is a very important result, and for objective problems you must remember it. I have not derived this result, but I am suggesting you must remember it. What will be the time period when oscillation is not a small oscillation, or you can say theta is not very small? In that condition, what will be the time period? And another remarkable fact is what? You can see the time period depends on the amplitude theta naught. Although in case of a small oscillation, the time period of oscillation is completely independent of amplitude. But in this case, time period depends on amplitude. Okay. So in case of oscillatory motion, time period will be a function of amplitude. But in case of simple harmonic motion, time period is not a function of amplitude. It is independent of amplitude. Okay. Hope you are getting the things, and definitely you are enjoying. Now again you can see, since t prime is equal to t times 1 plus theta naught square over 16. Since theta naught square over 16 is a positive number, and if you will add any positive number in 1, you will get a number greater than 1. And so t prime is equal to t times a number greater than 1. So definitely this t prime is greater than t. So I have written here, you can see t prime is greater than t, and it depends on amplitude. Okay. Now third important fact is what? This result for time period 2 pi root over L by G, this holds only when L is much smaller than R, as I have told you earlier, where R is the radius of the earth. Now we will see what will happen to this time period when L is not much smaller than R, but L is comparable to R. Then what will be the time period and how we can calculate that time period? This is our problem. Okay. So you can say that this formula which we have obtained was valid only when the length of the pendulum was much smaller than the radius of the earth. Okay. And when L is much smaller than R, then you know the acceleration due to gravity G always remains vertical. However, if the length of the pendulum is comparable to radius of the earth, then G will not remain vertical, but it will be directed towards the center of the earth. Okay. So here I am just going to calculate the time period when the L is comparable to R. Okay. And so for this you can see this figure. I have again shown a simple pendulum suspended from this point S. Okay. And here is your bob. You can see, let us say this is at a point A. Okay. At a point A. And this is point B, let us see. Okay. Now, since the length of the pendulum is very large, it is comparable to R. This may be greater than R. This may be even equal to R. Okay. So in this condition, if the bob is at this position, and I have shown in this figure this sphere which represents the earth, you know, in that condition, the force of gravity, that is weight of this bob, will act towards the center of the earth, because the earth always attracts a body towards its center by gravitational force. So mg I have shown here acting in the direction this AO. This is the line of action of mg, not in vertically downward direction. Okay. Now again we have to find the equation of motion to prove that motion will be SHM, and again we have to if your aim is to show that motion is SHM, you have to consider the case of a small oscillation. So this theta, which is the angular displacement of the bob from the vertical position, that will be a small 2 in this case. Okay. Actually this when this bob will be just in vertical direction, then it will be in equilibrium position. Okay. Now for getting the torque due to the force mg, again we have to find the perpendicular distance of the line of action of this mg from the point of suspension, and for this I have proceed this line of action of mg, and I have dropped a perpendicular, this sp. sp is the perpendicular drawn on the line of action of mg from the point of suspension. Okay. So this angle at P is equal to pi by 2, that is 90 degree. For calculation, I have considered that this angle SOA, you can see I have marked it here, SOA, this is equal to pi. I have considered it for calculation. Okay. And I have drawn a perpendicular AB, and I have also considered that AB is equal to X. I have considered it. Angle SOA or SOP, you can say SOP is equal to phi. I have considered. Okay. Now see this figure. A triangle, you can see the triangle SOA. This phi and theta are the two interior angles of this triangle. So according to the elementary geometry, this angle SOP, that is this angle, this will be actually equal to theta plus phi, because exterior angle is equal to sum of the corresponding interior angles according to geometry. So I have marked here that this angle is phi, theta plus phi, and this angle, which is vertically opposite angle, that will be also equal to theta plus phi. Okay. You can see. Now for getting the value of torque of force mg with respect to point S, I have drawn this perpendicular SP, and you know what will be the torque. Torque due to this mg will be equal to mg time SP. Okay. Again, this torque has a tendency to bring this bob towards the equilibrium position or to decrease the value of theta. So it is of restoring nature, and to indicate the restoring nature, again here minus sign has been substituted. So tau is equal to minus mg into sp. Okay. Minus mg into sp. Now we can find the value of sp from this figure. From the triangle SAP, you can see. If your aim is to find sp, let us find sine theta plus phi. What will be sine theta plus phi? You can see. Actually, this will be equal to SP divided by SA. You can see the figure. This angle is 90 degree. So SA is the hypotenuse and SP is the perpendicular. And SA, you know, is equal to L. This is length of the pendulum. So SP will be equal to what? This is L times sine theta plus phi. Theta plus phi. So tau is equal to minus mgl sine theta plus phi. Again, as I have told you earlier, that we are going to calculate the time period or discuss the motion under the limiting condition of a small oscillation. So even in this situation, we consider theta is very small. And if theta will be very small, this phi will be also very small. And so you can say that this theta plus phi is very small. And so sine theta plus phi can be written equal to theta plus phi. Okay. So tau is equal to minus mgl times theta plus phi. Now I have taken here this theta as a common factor. So after taking theta as a common factor, you can see tau will be equal to what? This is minus mgl times 1 plus phi over theta times theta. Okay. Now tau is equal to minus mgl theta, and inside the bracket you can see these two angles. Sorry. Phi and theta. Phi and theta both are very small. So this phi can be almost equal to tan phi. Okay. Because when phi is very small, then sine phi is also equal to phi, tan phi is also equal to phi. Okay. Don't worry, the page has been turned, but this will be just okay. Now see. So phi can be approximated as tan phi, and see the figure. What will be this tan phi? Tan phi will be equal to x over r. X over r. Okay. So at the place of phi, you can write x over r. Again see this triangle ABS and find out the value of theta. As theta is also small, so you can write theta is almost equal to tan theta. And what will be this tan theta? From figure you can see this is equal to x over L. X over L. So at the place of phi you can write x over r, and at the place of theta you can write x over L. Okay. So see, I have written it here. You can see in this expression. At the place of phi there is x over r, and at the place of theta there is x over L. Okay. Now x will cancel out, and after simplification you will get this expression is minus mgl times 1 plus L over r times theta. And as you know, this torque is equal to I alpha. You know, you have used this relation. And I is equal to ml square, and alpha is equal to d2 theta by dt square. You have seen this. Okay. Now again we take in RHS L as a common factor. So in RHS there will be minus mgl square times 1 over L plus 1 over r times theta. Okay. Now you can see this ml square and ml square will cancel out in LHS and RHS. So d2 theta by dt square is equal to what? This is minus g times 1 over L into plus 1 over r times theta. Okay. Now this g times 1 over L plus 1 over r, this is a constant factor, and we substitute omega square at the place of this. So you can write this is d2 theta by dt square plus omega square theta equal to 0, where omega square is equal to this much. And again you can see this is nothing, this is simply the equation of angular SHM. So you can see when L is not small, but it is comparable to radius of the earth, even then in case of a small oscillation, the oscillation is simple harmonic motion. Okay. The oscillation is simple harmonic. Okay. And from this equation of motion, now you can find the value of the omega, which is angular frequency of the simple harmonic motion, and then you can get the expression for time period. So let us see. If you denote the time period of the pendulum in this case by the symbol t prime, then this t prime will be equal to 2 pi over omega. Okay, 2 pi over omega. Or you can also, you should write it omega prime square. That will be more appropriate. Okay, and omega prime square is equal to this much. Okay, so this will be 2 pi over omega prime. Okay, t prime equal to 2 pi over omega prime. Now, after substituting the value of omega prime, the expression for time period will be what? This will be 2 pi times a square root of 1 over g times 1 over L plus 1 over R. And you can see from this that this expression shows that this time period is smaller than the time period when L was much smaller than R. That is, in case of a pendulum of a smaller length, time period is smaller, and in this case time period is greater. Okay. Now, after getting, actually this is the general result for the time period of a simple pendulum. The previous result is actually a special case. You will see that actually this formula defined in equation A, you should remember it. And this is the general formula for the time period of a simple pendulum. This is the general formula. Although in practice, whenever you will ask any person what is the formula or what is the expression for time period, people commonly say that t is equal to 2 pi root over L by g. But you should see here that actually this formula is not the general formula for time period of a simple pendulum. But this formula which we have obtained here, this is the general formula. This will hold in any situation when L has any value, this will hold. Only restriction is that the oscillation should be small, theta should be small. Only there is this restriction. Okay. So this formula 2 pi root over L by g is not the general formula for time period of a simple pendulum. Now let us see some important facts or some limiting condition imposed on this general result. Now if you consider that length of the pendulum is much smaller than R, it means you are talking about your first situation. Then what will happen? Since L is much smaller than R, then mathematically you know 1 by L will be much greater than 1 by R. So in comparison to 1 by L, we can neglect 1 by R in this condition. And when you will neglect this 1 by R, your result will be what? Then time period t prime will simply become 2 pi root over L by g. So this result validate this equation A, because when we consider that L is much smaller than R, we get the same result as we have obtained earlier. Okay. Now we consider the just opposite situation. If you consider that length of the pendulum is much greater than radius of the earth. As radius of earth is very large, this is almost 6400 kilometer, and you are saying that length of the pendulum is much greater than R. It means mathematically you can say that L is tending towards infinity. And when L will tend towards infinity, 1 over L will tend to 0. And so, in this condition, t prime will be equal to 2 pi root over R by g. This is a very important result. And R is the radius of the earth, which is 6.4 into 10 to the power 6 meter. And if you take g equal to 10 meter per second square, then after calculation you will get that time period of a pendulum having infinite length is equal to 84.6 minutes. In fact, in practice, when you ask any student or any person what will be the time period of a simple pendulum when its length is infinite, people think that L is infinity, so when we will substitute this value of L in the expression t equal to 2 pi root over L by g, then time period will be infinite. But this is completely wrong. As you can see, when L is infinite, time period is not infinite, it is finite, and it is in fact 84.6 minutes. Actually, this is a very important result. We will learn in the forthcoming lecture when we deal with the motion of a particle passing through a tunnel through the center of the earth. And then you will see the motion of a particle dropped in a tunnel through the center of the earth will be also simple harmonic motion, and the time period of the simple harmonic motion of that very particle will be equal to this much, 84.6 minutes. And if you are talking about a satellite, or you can say an artificial satellite moving around this earth very close to the surface of the earth, then its time period is also found to be 84.6 minutes. So these are the similar situations, and we will see this thing in the previous lecture. Although the problem of artificial satellite I have already discussed in my playlist of classical mechanics, and you can see that video. Okay. Actually, this time period which we have obtained here by taking L tending towards infinity, which is 84.6 minutes. Actually, this is the highest, this is the maximum time period of a simple pendulum. So when you are asked a question, what may be the maximum value of time period of a simple pendulum, your answer will be what? Your answer will be 84.6 minutes. It is never infinity. Okay. Now, if you consider that L is comparable to R, it means L is not much less than R, L is not much greater than R, L is almost equal to R. And for example, we take L is equal to R. When the length of the pendulum is equal to radius of the earth, then what will happen? You can see this formula. When L will be R, this will be 1 over R plus 1 over R, that will be 2 by R, and so the expression for time period will be 2 pi times root over R divided by 2g. And when again you will substitute the value of R and G and simplify, you will get that this time period will be almost equal to 1 R. Okay. So time period of a simple pendulum having length equal to radius of the earth, that will be almost equal to 1 hour, that is almost equal to 60 minutes. And what is the maximum time period? Maximum time period is 84.6 minutes. Okay. So this was a brief concept of the simple pendulum as a angular harmonic oscillator. I think definitely you have enjoyed this lecture, and so keep watching because the forthcoming videos will be just like this. Okay. Thank you very much.